Hiya. So in this video, we're going to be looking at functions in discrete conditional expectation. Um, so let's kind of look at this and kind of see what we're kind of thinking about. So intuitively, when we're given x is equal to x, the basic idea is that we want to replace all our random variables with our x. So that's basically what we know, right? We're saying x is equal to x, right? And so this is like, we kind of saw this before in a reverse setting, right? Remember when we saw dx and I made this become dx when I was looking at expectation, right? And so a very similar thing is going to happen in this world. And basically the idea is, well, what happens if we have some function g of x, y, and we're given x is equal to x? It turns out this is perfectly okay. So basically what we want is g of x, y, given, oh, this is a big y, not a little y, given x is equal to x. In this case, what we can do is, well, we know that big X is equal to x, so we can just say, well, g of little x, y, given x equals x. Here I need to keep this, or else it wouldn't make sense, right? If I do little x equal little x, well, now we kind of lose information. So we can't really lose information, but we can convert this first little x, and that's okay. This is super useful because like we do these functions a lot. Like for example, if I were to do e of x times y given x is equal to x, well, what this means is I can convert this big X into a little x given x equals to x. And by linearity, remember we can actually take this little x, since it's a number, and bring it out front. So this is just x times y given x equals x. So it kind of makes life a lot easier. So it's like a nice thing to kind of know that you can play around with these things. Now, if you want, you can actually try this and figure this out using the equalities. So if you're bored and have something to do, I would say try it out and test it out and see what this gives. But basically what this implies is that if I look at this, x, y given x, so I don't look at any particular x, well, this is just going to give me this, that I can just replace this. Remember here that these are random variables, right? This is one random variable and this is another random variable. They're both random variables. Likewise, if we look at linear equations, what I have is ax plus by given, what am I doing here? I'm doing x equals to x. This is just e of, well, ax plus by. Y I can't convert because I don't know what that is equal to, but I know x is equal to little x, so I can convert that. So here we get ax plus b expected value of y given x equals x. In other words, another way of looking at this, ax plus by given x, this is basically telling me that this is equal to ax plus b of the expected value of y given x. So you can kind of see that like we can use these to manipulate things and stuff. And this actually helps us with a lot of details. So let's actually look at an example to kind of see how this helps. So let's look at this. Here we have x and y are independent, and we're trying to solve the expected value of x plus y is equal to x. X is equal to x. So this first part, this should be fairly easy, right? So we have e of, well, not easy, but like given what we just went over, this should be not too hard. So this big X we can convert to a little x, x plus y, given x equals x. And we can pull this out, right? So this is just x plus the expected value of y given x equals x. So now all that's really left is to calculate what this is equal to. What we know is that y and x are independent. So no matter what x is equal to, y is not, it's not dependent on x. So the expected value of y shouldn't change based off x. And we'll actually see this, right? So let's actually try this. Y given x equals x. What we're thinking, we think since x and y are independent, y, that this equals this, right? This is kind of what we're saying. We think this is true. So let's actually show this. Let's see if this is actually true or not. So by definition, we're going to look at all y. Y times p of y equals y given x equals x, right? Here, we know that in this case, you can right away notice that I can remove the x equals x here. But if you don't, you can plug this into our conditional probability formula to get this. At this point, you can use independence to split them apart. Y times p of y equals y times p of x equals x over p of x equals x. These will cancel. And I'm left with all y p of y equals y. And this is literally just the definition of e of y. So we basically showed kind of what we wanted to show, that these are basically the same, that there's no difference. In other words, what we have is the expected value of x plus y given x equals x is just equal to x plus the expected value of y given x equals x, which is just x plus the expected value of y. And that's kind of where we're going to end. I didn't give you what these numbers are, or else you could just plug them in. If you knew the expected value of y, you could just plug this in. But this is much nicer than this, right? Like, this is not a fun thing to read or do. This is much more manageable, and we have much more tools to kind of solve, right? If this was geometric, if y was geometric, this would be easy. So yeah. So I will end this video here. And in the next video, we're going to start talking about covariance. And this will lead to like the final kind of parts of this class. So I'll stop here, and I'll see you in the next video for covariance. Bye.